You're probably wondering why I told you not to watch this video. And I wanted to try an experiment. I wanted to see if people would actually watch the video after receiving a message not to do so. It's sort of a reverse psychology thing. And it's been said that if you tell someone not to do something, they will actually do it, which is weird, but I wanted to try this out and see, if this will actually work. And so I would like to ask you to do something. If you have a moment, that is, if you're not too busy, and that is to post a comment in terms of why you chose to watch this particular video. Was it because you wanted to learn organic chemistry, or was it out of curiosity because the video told you not to watch it? What was the reason? Out of all of the other videos that you could have clicked on, why did you choose to watch this particular video? So let me know in the comment section if you have time. Now, the title of this video is Organic Chemistry, so I'm going to stay true to that and teach you OrgoChem. So for those of you who want to get an introduction into organic chemistry, if you're about to take it in the next upcoming semester, you came to the right place. Let's begin. The first thing I'm going to do is teach you how to draw Lewis structures of common compounds. So let's review some basic things in the periodic table. So in group 1, you have elements like hydrogen, lithium, sodium, and these elements, they contain one valence electron. That is the number of electrons in the outermost energy level. And as such, these elements typically form one bond. Whenever you see hydrogen in a molecule, keep this in mind. Hydrogen can only form one bond. If you were to see beryllium, which is in group 2, it has two valence electrons that it can give away. You'll see typically it will form two bonds. Boron, which is on this side, on the right side of the periodic table, is in group 3A. It likes to give away 3 electrons, and so it tends to form 3 bonds. Not always though, but ideally. If it's neutral, it's going to form 3 bonds. If it has a negative charge, it's going to form 4 bonds. But for elements or compounds that don't have a charge, the number of valence electrons is related to the number of bonds that they form. Carbon, for example, has 4 valence electrons, and it likes to form 4 bonds. Now, as you get to the right side of the periodic table, towards the nonmetals, the trend changes. Nitrogen, for example, has 5 valence electrons, but in its neutral state, when it doesn't have a charge, it likes to form 3 bonds. And the reason for this is because the elements on the right, the nonmetals, they like to acquire electrons. They want to get 8 electrons to satisfy the octet rule. And so that's why nitrogen likes to form 3 bonds, so that it can get those 3 electrons it needs to get to 8. So I'm going to put it in red, that nitrogen likes to form 3 bonds. Oxygen has 6 valence electrons. It needs 2 more to get to 8, so oxygen likes to form 2 bonds. Fluorine has 7 valence electrons. It only needs 1 more to get to 8, so fluorine likes to form 1 bond. And this is true of the other halogens, like chlorine, bromine, and iodine. Ideally, they like to form 1 bond. Now, there are exceptions to this rule, particularly if you have a molecule where bromine or chlorine is the central atom. In that case, it may form more than 1 bond, but typically in organic chemistry, you'll see that most of the time, these elements like to form 1 bond. Elements under oxygen like sulfur, selenium, they like to form 2 bonds. Phosphorus, it likes to form 3. Now remember, these are just general trends that you'll see in organic chemistry. Now let's focus on these 2 elements, nitrogen and oxygen. So remember, nitrogen likes to form 3 bonds if it doesn't have a charge, if it's neutral. And oxygen likes to form 2 bonds in its neutral state. So we can illustrate that with ammonia. Ammonia, NH3, has 1 lone pair, and 3 bonds. In this state, nitrogen doesn't have a charge, and so it has its ideal number of 3 bonds. Now, when nitrogen loses a hydrogen, it's going to have 2 bonds, but it's going to have a negative charge. So in this case, it doesn't follow the trend because it's not in its neutral state. It has a charge. Or, if nitrogen acquires a hydrogen atom, or rather a hydrogen ion, it's going to acquire a positive charge. Once again, it doesn't have its ideal number 3 bonds, and so that's why it has a charge. So that general rule, where you can look at the table and determine the number of bonds that an element prefer to have, that rule applies when the element is in its neutral state. Now let's consider the structure of water, of H2O. In this molecule, there is 1 oxygen atom and 2 hydrogen atoms. As you can see, in this structure, oxygen doesn't have a charge because it has its ideal number of 2 bonds, which is what it needs to get to 8 electrons. Now, if we were to draw hydroxide, it will have a charge, a negative charge, because it doesn't have its ideal number of bonds. It only has 1 bond. Now, if it has more than its ideal number, it's going to acquire a positive charge. So whenever oxygen has 3 bonds, it's going to have a positive charge. Whenever it has 1 bond, it will have a negative charge. Now, for those of you who want to understand how this works with more examples, including the exceptions, check out a video that I created on YouTube. It's entitled Lewis Structures. It's a very big video. It's about 2 hours long, so you can't miss it. And if you type in Lewis Structures Organic Chemistry Tutor, it should come up. But in that video, I go deeply into why this works the way it does, with many examples, as well as the exceptions, and understanding the reasons behind why those exceptions exist. So if you want a deeper understanding of that, feel free to take a look at that video when you get a chance. Now, let's review a few things. When you see nitrogen as an element in a Lewis structure, know that it likes to form 3 bonds, and it will have 1 lone pair in its neutral state. If you were to see oxygen, it typically has 2 bonds and 2 lone pairs. Or if you see another element with 2 bonds, then you know that there's going to be 2 lone pairs missing. Now, if you see an element like fluorine with 1 bond, then you need to know that it has 3 lone pairs on it. And if you see carbon, make sure you know that carbon likes to form 4 bonds. In organic chemistry, you're going to see a carbon a lot, so make sure you know this. Let's go over some examples. Let's say if we wish to draw the Lewis structure of methane. How can we do so? Now remember, carbon likes to form 4 bonds, and hydrogen likes to form 1 bond. So the only way to put this together is to draw 4 bonds around the carbon atom, and each bond is attached to 1 hydrogen atom. And so that's how we can draw the Lewis structure of methane. Now what about ethane? CH3, CH3. So when you see a condensed structure like this, draw it from left to right. So starting with the first carbon on the left, let's draw that. It has 3 hydrogen atoms attached to it. And so let's draw the 3 hydrogen atoms starting from the left. Now, it's attached to another carbon atom that has 3 hydrogen atoms attached to it. And so that's how you can draw the Lewis structure of ethane. Now, let's say if we want to draw the Lewis structure of propane, CH3, CH2, CH3. So starting with the carbon on the left, it has 3 hydrogen atoms attached to it. Then it's attached to another carbon, that is the CH2 carbon. So that carbon has 2 hydrogen atoms attached to it. Next, it's a CH3. So we have another carbon atom with 3 hydrogen atoms attached to it. And so that's how you can draw Lewis structures of alkanes. An alkane is an organic molecule that consists of carbon and hydrogen where there are no double bonds or triple bonds. An alkane is said to be saturated. It is filled to the limit with hydrogen atoms. It contains the maximum number of hydrogen atoms it can possibly hold. And so this is a hydrocarbon that is said to be saturated. Now what about the Lewis structure C2H4? How can we draw it? So we know that there are two carbons, and those two carbons have to be attached to each other. But we can't put the 4 hydrogen atoms on the right side because carbon cannot form 5 bonds. So that's not going to work. When you see a situation like this, the best thing to do is to distribute the number of hydrogen atoms equally among both carbon atoms because they're the same element, and so they're going to have the same affinity for the hydrogen atoms. So it makes sense that you should share them equally. So we're going to put 2 hydrogen atoms on the right side and 2 hydrogen atoms on the left side, keeping in mind that hydrogen can only form 1 bond. Now, at this moment, carbon only has 3 bonds. So if we were to highlight it, 1, 2, 3. But carbon needs to have 4 bonds. The only way to rectify the situation is to put a double bond between the carbon atoms. And so now every carbon atom has a total of 4 bonds around it, and every hydrogen atom has 1 bond. So once those conditions are met, you know you have the right Lewis structure. Now this particular molecule is known as an alkene. An alkene is a functional group where the organic compound has a double bond. It's also known as an unsaturated compound. The reason why it's unsaturated is because, unlike an alkane, it does not contain the maximum number of hydrogen atoms that it can hold. So it's unsaturated. Now let's try this one. C2H2. Go ahead and draw the Lewis structure based on the previous example. So in this case, there are 2 carbon atoms, and there's 2 hydrogen atoms, which we'll place them out on opposite sides with symmetry. Now, hydrogen can only form 1 bond, and carbon likes to form 4 bonds. So the only way we can make that work is by putting a triple bond in the middle. And so this is known as an alkyne. It's also an unsaturated hydrocarbon. Alkynes contain triple bonds. Now you need to know that triple bonds are very strong. They're stronger than single bonds, but in terms of length, they are very short. Single bonds are very long, but they're weaker. Triple bonds are stronger, but they're shorter. Now, the way I like to think of the strength of a triple bond is like a pencil. It's easy to break 1 pencil, like a single bond, but it's harder to break 3 pencils at the same time, because 3 pencils are stronger. And the same is true for a triple bond. It's very difficult to break all 3 bonds compared to just breaking 1 bond. So triple bonds have more bond strength than an individual single bond. Now, I want to go over some common names of alkanes. So the first one, which we talked about already, this is known as methane. The second one, which contains 2 carbons, C2H6, this is known as ethane. Alkanes, they have the general formula CnH2n plus 2. Now, we talked about C2H4, and so this was an alkene, but notice that it has 2 carbons. So this is called ethene. And the general formula for an alkene with 1 double bond is CnH2n. Now the next one that we went over was an alkyne. And the example that we use was C2H2. The general formula for an alkyne is CnH2n minus 2. And so this particular alkyne has one triple bond, and any other alkynes with this formula will have only one triple bond. Now, when dealing with 3 carbons, the name is propane. So if we have C3H6, this would be propene. It would be an alkene. Or if we have C3H4, that would be propyne, because it has a triple bond, and so it's an alkyne. Now, for an alkane with 4 carbon atoms rather, this is known as butane. And for a molecule with 5 carbon atoms, this would be pentane. And for an alkane with 6 carbon atoms, this is known as hexane. C7, that corresponds to heptane as an alkane. So that's C7H16. C8H18, this is known as octane. C9H20, this is known as nonane. And C10H22, this is called decane. Deca is 10, nona is 9, octa is 8, hepta is 7, hexa is 6, penta is 5, and so forth. Now let's try another example. CH3OH. How can we draw the Lewis structure of this particular compound? So starting from the left, we have a carbon atom that is attached to 3 hydrogen atoms, each of which can only form a single bond. Now we do have an oxygen atom, and if you recall, oxygen likes to form 2 bonds, and it's going to have 2 lone pairs. So that's how we can draw the Lewis structure for this molecule. And whenever you see an OH group at the end, the functional group is known as an alcohol. Now, if you recall, a 1-carbon alkane is known as methane. But now, the functional group is not an alkane anymore. It's an alcohol. So, instead of saying methane, this is going to be called methanol. But as you can see, the structure of the name meth is still there because methyl or metha is associated with 1 carbon atom. The OL tells us that it's an alcohol rather than an alkane. Let's consider another example. CH3, CH, in parentheses, OH, and then CH3. So how can we draw the Lewis structure of this particular molecule? And at the same time, what do you think the name of the molecule will be? So starting from the left side and working our way towards the right side, on the left we have a carbon with 3 hydrogen atoms. And then we have another carbon with a hydrogen atom, which I put at the bottom. And then it also has an OH. When you see that in parentheses, that means that the previous carbon is attached to an OH group. So we can draw O and then H. And remember, oxygen, when it has 2 bonds, will typically have 2 lone pairs. And then to the right, we have a CH3. So every carbon atom in this molecule has 4 bonds. Every hydrogen atom has 1 bond, and oxygen has its desired number of 2 bonds. And so by understanding those basic principles, it will help you to quickly draw the Lewis structure of an organic molecule. Now let's talk about naming this molecule. So anytime you see an OH group, you know you have an alcohol on your hands. Now R, that's basically the rest of the molecule, so you don't have to worry about it. But anytime you see the OH group, it's an alcohol. Now, if we count the number of carbon atoms, let's call this carbon 1, 2, and 3, there are 3 carbon atoms, which is associated with the name propane. Prop is associated with 3. Now, we do have an alcohol, so we're going to take off the E and add OL. So this is going to be called propanol. Now, the last thing we need to do is identify the position of the alcohol, or the OH group. The OH group could be on carbon 1, but it's on carbon 2, and so we need to specify the position of the OH group in this molecule. So this is going to be called 2-propanol. If the OH group was on carbon 1, it would be called 1-propanol. So this is how you can name this particular alcohol. Now, let's talk about ethers. Ethers are the next functional group that you need to be familiar with if you're going to take organic chemistry. And let's start with this example, CH3OCH3. So let's begin by drawing the Lewis structure. So on the left, we have a methyl group, or a CH3 group, and the carbon is attached to an oxygen, which is attached to another carbon atom with 3 hydrogen atoms on it. And when dealing with oxygen, whenever it has 2 bonds, it's going to have 2 lone pairs. And so that is the Lewis structure of this particular ether. Now, to name it, we're going to use the common name first. On the left side, we have a methyl group, and on the right side, we have a methyl group. And since we have 2 methyl groups on this ether, we can call it dimethyl ether. Di means 2. Now, what about this particular ether? What is the common name for it? CH3CH2OCH3. Let's not worry about the Lewis structure for this example. Now, on the left side, we have 2 carbons, so that is an ethyl group. And on the right side, we have a CH3, so that is a methyl group. Now, to write the common name, we need to put this in alphabetical order. So it's going to be called ethyl methyl ether. So that's the common name for it. Now let's focus on the IUPAC name of this particular ether. So I'm going to draw it differently. So attached to this carbon, we have an OCH3 group. So you can call this the substituent. And it's located on carbon 1. This is the parent chain. It's the longest carbon chain in that molecule. So this group right here is called ethane because we have 2 carbons. And the OCH3 group as a substituent is known as a methoxy group. So another way in which you can name this molecule, you can say it's 1-methoxy ethane. Now, it really doesn't matter if the OCH3 group is on carbon 1 or carbon 2. Because no matter which way you count it, the first one is going to be carbon 1. So if the OCH3 group was on this carbon, it would still be 1-methoxy ethane. So therefore, the 1 is not necessary in this case. So we could simply call it methoxy ethane. Let's work on another example with ethers. So go ahead and name this particular ether, both the common name and the IUPAC name. So let's start with the common name. On the left side, we have a propyl group, and on the right side, we have an ethyl group. So putting it in alphabetical order, E comes before P, so it's going to be ethyl, propyl, ether. Now I'm going to redraw the structure like this. So the longest chain is 3 carbons, and I'm going to put the substituent, the OCH2CH3 group, on top. Now, if you want to, you can convert this to a line structure. These 3 carbons can be represented like this. And so every endpoint that you see here represents a carbon atom. So at the last one on the right, we can write the OCH2 CH3 group. So let's call this carbon 1, 2, and 3. You want to number it in such a way that the substituent is given the lower number. So you don't want to number it this way, because the substituent will be on carbon 3. Rather, you want to count it from right to left in this example, so that the substituent is on carbon 1. It's given a lower number. So this right here is called an ethoxy group. So instead of a methoxy, it's ethoxy, since we have 2 carbons in that substituent group. And we're still dealing with an ether. Now it's located on carbon 1, and the longest chain is a 3-carbon chain, which is going to be called propane. So to put it together, it's going to be called 1-ethoxy propane. And so that's how you can name that particular ether. Now, how would you draw the Lewis structure for this molecule? Go ahead and try that. So let's start with the left side. So we have a methyl group that is a carbon with 3 hydrogen atoms, and that's attached to a CH2, which is attached to a carbon. Alright, so now let's stop. Let's focus on what we have here. Now remember, carbon likes to form 4 bonds, and oxygen likes to form 2 bonds. So what can we do here? Well, we can't write it like this, because this is not going to work. The carbon will only have 2 bonds, and so that is not the ideal situation that we want. To make this work, the only way in which the carbon atom will have 4 bonds and the oxygen atom will have 2 is to put a double bond between the carbon and the oxygen. That's the only way this is going to work. And so as you can see, every carbon atom has 4 bonds, every hydrogen atom has 1 bond, and the oxygen has 2 bonds and 2 lone pairs. This is known as a carbonyl functional group. Whenever you see a C double bond O, it's called a carbonyl functional group. Now, this particular molecule also has a special name. It's called a ketone. Whenever you have a carbonyl functional group in the middle of the chain, that is, it's not at the end, it's called a ketone. If it's at the end, let's say at the last carbon or at the first one, it's known as an aldehyde. Now, let's go ahead and name this particular ketone. So which way should we count the carbon atoms? From left to right or right to left? If we count it from left to right, the carbonyl group will be on carbon 3. But if we count it in the other direction, from right to left, it's going to be on carbon 2. And so we're going to go with that direction. So this is going to be called 2-butanone. Now, if the carbonyl group was on carbon 1 or 4, as we said before, it's going to be an aldehyde, not a ketone. If the carbonyl group was on carbon 3, and we would have to count it this way, it would still be called 2-butanone. So therefore, the 2 is not necessary. We can simply call this butanone, because if the carbonyl group was on this carbon or on this carbon, you would simply count it in different directions, but the result will be the same. It would still be called butanone. In a situation like this where the result is the same, you really don't need to write the number. It's not necessary. Now let's try another example. How can we name this particular molecule? So we have a line structure, and we need to count it starting from the right side, because the carbonyl group is closer to the right. And so we could see it, it's on carbon 3. And we still have the ketone functional group. Now for 7 carbons, we have the name heptane. But because is a ketone, instead of saying heptane, we're going to say heptone. Or not heptone, but we're going to drop off the E and add one. So it's heptanone. And we're going to put a 3 in front of heptanone because the carbonyl group is located on 3. Now this time we need to specify where the carbonyl group is located. So the answer is 3-heptanone. Now let's move on to our next example. Let's draw the Lewis structure of CH3CHO. Anytime you have this, if you see CHO rather than OH, OH is typically associated with an alcohol. But CHO, when you see that, you have an aldehyde. This is very specific for an aldehyde. Now let's draw it. So let's start with the methyl group on the left. And so we have a CH3 attached to a carbon. Now how do you think we can write the Lewis structure of CHO? Now we can't write it like this because hydrogen cannot form 2 bonds. And it doesn't make sense to write it like this, like an alcohol, because carbon will only have 2 bonds. So we need to make a carbonyl group. If we do it like this, now carbon has 4 bonds, oxygen has its desired number of 2 bonds, and hydrogen has 1. So anytime you see CHO, it's basically a carbonyl group at the very end. Now, we have a 2-carbon molecule, so instead of saying ethane, we're going to drop off the E and replace it with Al. And so that's how you name an aldehyde. So this is ethanal. Let's try another example. So how can we name this particular aldehyde? So this is going to be carbon 1, 2, 3, 4, 5. So instead of saying pentane, we're going to drop off the E and replace it with Al. It's pentanal. Now we don't need to say 1-pentanol because the aldehyde functional group is always at the end of the chain. So the 1 is always going to be there, unless it's a substituent. Now what about this one? CH3, CH2, COOH. So whenever you see this functional group, COOH, you have something known as a carboxylic acid. It's a weak acid, but that's the functional group for it. So if you see RCOOH, sometimes you'll see it as RCO2H, and it's the same thing. It's a carboxylic acid. So let's go ahead and draw the Lewis structure. At least just the right side. So the left side, I'm going to leave it as CH3, CH2 because you know how to draw already. Now for the last part, we have a carbon. We have 2 oxygen atoms, one of which is going to be a carbonyl group, and the other part is going to be an OH group. And so carboxylic acid is the combination of a carbonyl group and a hydroxyl group, or an OH group. And so that's how the Lewis structure will look like if you expand it. Now to name it, we have a 3-carbon carboxylic acid. So 3 carbons is associated with the word propane, but instead of saying propane, we will drop off the E and add oic. So it's called propanoic acid. And that's how you could name the carboxylic acids. Let's try this example. Go ahead and name this particular carboxylic acid. So we have a total of 8 carbons, which is associated with the name octane, but it's going to be called octanoic acid. And as you can see, the carboxylic acid is always on position 1. Thus, there's no need to say 1-octanoic acid. It's simply octanoic acid. Next up, we have this molecule, CH3, CO2, CH3. This is known as an ester. So if you see this functional group R and then COO and then another R group, you have an ester. So to draw the middle portion, we have a carbon with a carbonyl group and an oxygen that's attached to a CH3. And so typically you'll see this associated with esters. The difference between an ester and a carboxylic acid is in a carboxylic acid, this whole group will be a hydrogen. If it's a carbon with some other stuff attached to it, then it becomes an ester. Now to name it, we're going to start with this side. The carbon that doesn't have two oxygens attached to it. So this group is a methyl group. Now on the left side, we have two carbons, including the one that has two oxygens. And so that group is called, instead of saying ethane, it's ethanoate. But when naming esters, the alkyl group goes first. So it's going to be called methyl ethanoate. So that's how you name this particular ester. Now the next functional group is an amine. And so for amines, you'll have the RNH2 group. So let's go ahead and draw that particular structure. So here is the ethyl group, and we have a nitrogen attached to two hydrogen atoms. And as we recall, nitrogen likes to form 3 bonds in one lone pair. So that's how we can draw this particular amine. And the common name for it in this example is ethyl amine, because we have an ethyl group attached to an NH2 group. Now, if you're dealing with IUPAC nomenclature, the NH2 group as a substituent is called amino. So you can also say this is amino ethane. Now let's say if we had a longer chain and we have the NH2 group on carbon 2. So for a 5-carbon chain, this would be pentane. But we can say 2-amino pentane. So that's how we can name that particular amine. Now the next functional group you need to be familiar with is an amide. And the amide is similar to an amine. The only difference is there's a carbonyl group between the R group and the NH2 group, making it an amide. So this particular amide with 4 carbons is going to be called, instead of saying butane, we're going to drop off the E and add amide. So collectively, we're going to call it butanamide. Now, some other functional groups that you want to be familiar with is the nitrile. Another one you'll see in organic chemistry is the acid chloride. And finally, another one is the benzene ring, also known as an aromatic ring. So this benzene ring, the formula is C6H6. Every carbon atom has 1 hydrogen atom attached to it. So that's a benzene ring, also known as an aromatic ring. So those are some other functional groups that you want to add to your list. Now let's move on to something called formal charge. You need to be able to calculate the formal charge of an element. So let's start with oxygen. What is the formal charge of the oxygen shown in the picture? Is it +1? Is it -1? Is it 0 or neutral? Is it -2, +2? What is it? To calculate the formal charge of an element, it's going to equal the number of valence electrons in the free element minus the number of bonds and dots that you see in the picture. So naturally, oxygen has 6 valence electrons. It's in group 6A of the periodic table. In this example, it has 1 bond, as we can see here, and there's 3 lone pairs, which is equivalent to 6 dots. And so 1 plus 6 is 7, and so we have 6 minus 7, which is -1. And so this oxygen has a negative charge. So anytime you see oxygen with 1 bond and 3 lone pairs, you need to put a negative formal charge on it. Now what about this example? So let's say we have R, O, H, and another H with a lone pair. What is the formal charge on oxygen? So using the same formula, the formal charge is going to be the number of valence electrons minus the sum of bonds and dots on that element. So the formal charge for oxygen is going to be the 6 valence electrons that it has, and in this structure we could see a total of 3 bonds and 1 lone pair, or 2 dots. Now 3 plus 2 is 5. 6 minus 5 is 1. So in this case, whenever oxygen has 3 bonds and 1 lone pair, it's going to have a positive formal charge. Now let's try nitrogen. So what if we have R, N, H with 2 lone pairs? What is the formal charge on the nitrogen atom? Go ahead and try that one. Nitrogen is found in group 5A of the periodic table, so it has 5 valence electrons. In this structure, it currently has 2 bonds, and it has 4 dots, or 2 lone pairs. So 2 plus 4 is 6, and 5 minus 6 is -1. And so the nitrogen has a negative formal charge in this example. Another topic that you will encounter in your first semester organic chemistry course is resonance structures. So here's what a typical problem will look like. You'll be given a structure. In this case, this is ethanoate, also known as acetate. And you're told to draw the resonance structure of the one on the board. And here we have a negative formal charge on the oxygen. To draw a resonance structure, what you need to do is you need to realize that you're allowed to move electrons, but not atoms. And you need to use something called curve arrow notation to show it, to show the movement of electrons. A full arrow represents the flow of 2 electrons. A half arrow represents the flow of 1 electron. So we're going to take this lone pair, these 2 electrons, use it to form a double bond, also known as a pi bond, and we're going to break this pi bond and put 2 electrons on the other oxygen. And we could use a double arrow to indicate that the next structure is a resonance structure. And so this is how the other resonance structure is going to look like. So now the oxygen on the right has 2 lone pairs because it lost 1, and the other one it gained 1, so it has 3. And so that's how we can draw the resonance structure of acetate. Now let's try another example. Let's draw the resonance structure of an amide. Go ahead and try it. What we could do is take a lone pair from the NH2 group, form a pi bond, and then break the pi bond of the carbonyl group. And so the resonance structure will look something like this. In this case, the oxygen now has a negative formal charge, and the nitrogen has a positive formal charge. By the way, which of these 2 resonance structures is the major resonance contributor? Which one is more stable? In the other example, In both resonance structures, the oxygen had a negative charge, so they were equally stable. And this one is different. In the first example, both the oxygen and the nitrogen were neutral. Now, the oxygen has a negative charge and the nitrogen has a positive formal charge. And whenever you see this situation, whenever you have separation of charge, it creates a less stable situation. And so the less stable resonance structure is known as the minor resonance structure, and the more stable one is known as the major resonance structure. The actual molecule is really a hybrid between these two. However, the actual molecule, it looks more like the major resonance contributor and less like the minor resonance contributor. Even though it's somewhere in between, it's going to look more like this molecule. Now, what about this example? So let's say we have a double bond, actually two double bonds, and a carbon with a negative charge. A carbon with a negative charge is known as a carbanion. A carbon with a positive charge is known as a carbocation. So in this case, how can we draw the Lewis structure, or rather the resonance structure of this particular ion? What we need to do is take the lone pair and move the electrons towards the double bond. We can break this pi bond, put 2 electrons on this carbon, and so the first resonance structure that we can draw will look like this. And now we have the negative charge on that carbon. And then we could repeat the process. We can move the negative charge 2 carbons further to the left. And so in this example, we can draw a total of 3 resonance structures, including the original one. And so anytime you see a lone pair next to a double bond, that's what you can do if you wish to draw the resonance structure. Now, let's say we have a 6 carbon ring with a positive charge on the outside. Draw the possible resonance structures for this one. Now, in this case, we're going to move the pi bond to or towards the carbocation. So the first resonance structure that we can draw will look like this. So now the pi bond is over here, and the plus charge is going to move to the carbon that lost the bond, which is that carbon at the top. So like the negative charge in the last example, you'll find that the positive charge will jump every 2 carbons towards the double bond that moved. And so we could break this pi bond, move it here, and this will give us a new resonance structure, which looks like this in this case. So now the plus charge is at the bottom left, and we can draw one more resonance structure for this example. Let's take this double bond, move it here. So that's a basic intro into resonance structures. Now, for those of you who want more examples in this topic, feel free to check out my new organic chemistry video playlist. I do have an old one, but check out the new one. And I have some videos on resonance structures, drawing Lewis structures, naming compounds. So you can check that out if you want to. I'm going to paste the link of the new organic chemistry video playlist in the description section of this video. So once you access that playlist, you could find the specific topic that you need help with. So feel free to take a look at that when you get a chance. Now let's spend a few minutes naming alkanes. How would you name an alkane that looks like this? Let's focus on IUPAC nomenclature. The first thing we want to do is count the parent chain. And we have a methyl group on carbon 3. So first let's name the parent chain, which is hexane, because it has 6 carbons. And we have a methyl group on carbon 3, so this is going to be called 3-methylhexane. And so that's how we can name that particular alkane. Now what about this one? We need to number it from left to right. You want to number it in such a way that the substituents, the two methyl groups, contain the lowest numbers possible. So right now we have a methyl on 3 and the other one on 4. If we were to name it in the other direction, or rather count it in the other direction, we would have a methyl group on 4 and 5. 3 and 4 is less than 4 and 5. So always number the carbon atoms in such a way that the substituents have the lowest numbers possible. So we have a 7-carbon parent chain, and so it's going to be called heptane. And we have 2 methyl groups, so it's going to be dimethyl because we have 2 of them, and it's located on 3 and 4. So it's going to be 3, 4 dash dimethyl heptane. You should use a comma to separate numbers, and use a hyphen to separate a number and a letter when naming alkanes using IUPAC nomenclature. Now let's try another example. So let's say we have these 2 groups. How would you name it? Now first, we need to decide which way to count. So let's count it this way. And let's write the name of the molecule that results. So if we were to count it this way, we would have a methyl on carbon 4, and this substituent has 2 carbons on it, and so that's going to be an ethyl group. So we have an ethyl on carbon 5. Now when putting it together, you need to put it in alphabetical order. So E comes before M. So this will be called 5-ethyl dash 4-methyl dash octane, or rather just octane, because we have a total of 8 carbons in the longest chain. Now suppose we counted it in the other direction. Let's see if that's going to make a difference. The only difference would be that instead of having a 4-methyl group, we now have a 5-methyl group. And instead of having a 5-ethyl group, we now have a 4-ethyl group. So it's going to be called 4-ethyl dash 5-methyl octane. So we still need to put the substituents in alphabetical order, but this option is better. If you could put the numbers in ascending order, it's always a better option. So this is going to be the correct IUPAC name. Now I'm going to end the video here. And if you want more examples on naming alkanes like this one using IUPAC nomenclature, you could search up my videos on YouTube, or you could find it in my new organic chemistry playlist, which I'll post a link in the description section of this video. And so if you want to find more examples on that, feel free to take a look at that playlist. So thanks for watching.